dear students, we were talking about postulates of quantum mechanics, and in the last few classes I talked about postulate 1, which was about wave function. I talked about postulate 2, which was about operators, and then I talked about postulate 3, which was eigenvalue equations. So all three postulates we did. Postulate 1 about wave function, postulate 2 was about operators, which we did in detail. Then postulate 3 we did, which was about eigenvalue equation. Okay. And I said you that in an eigenvalue equation, the last class I said you that if you have a function f x, say suppose 4x cube plus say 5x square plus 6, and if your operator is d dx, then what you do? You operate with this operator, d dx is the operator, then you operate with this function f x, and what do you get? You get 12x square plus 10x. Okay. So, when you operate with an operator, function changes, and this function, which was originally this one, became this one. Okay. But if you operate with the same operator d dx on a function, say exponential a x, then you get a x. So, the function does not changes, and if this happens, then this is called eigenfunction and this is called eigenvalue. Okay. And if you operate with an operator of energy on a wave function, the constant which you get is the value of energy, value of physical variable, which in this case is energy. So, energy value you get. If you operate with operator of momentum, you get certain values, say a, and this back, then this is the value of momentum, and so on. Okay. So, this we did in the last class. I gave you another example of a function a x square and d dx is the function. Then I said you that what you get is 2 a x into exponential a x square. So, now you get the constant, but the function changes. This becomes function f prime, where this is f. So, this is not an eigenvalue equation. So, 2a will not be the eigenvalue. Okay. So, this was postulate 3. In postulate 4, what we say is postulate 4 is about average value of a physical variable, or also called expectation value. So, postulate 4 is average value or expectation value postulates. Here what we do, we try to find out the average value of a physical variable if the wave function is known. Okay. So, in order to get this, the average value of a physical variable, say m is the physical variable, then the equation which we use is psi operator of m, psi star d tau from minus infinity to plus infinity divided by minus infinity to plus infinity psi star d tau. This is the equation for determining the average value, where this indicates average value, and m is the operator of physical variable for which we are calculating, or for which average value is to be calculated. If psi is a normalized function, then your average value will become d tau, because the denominator that is psi star d tau from minus infinity to plus infinity will be equal to 1, okay, because this is what is called normalization condition. Okay. So, this is the normalization condition, and we get this one. Now, why we are taking average in this fashion? Let's see how do we take the average of numbers. If you remember your primary school mathematics, then how do you calculate? So, suppose you have numbers 2, 2, 4, 4, 4, okay. So if you have numbers 5, 5, 5 and 5, and if somebody asks you find the average value of these numbers, we say xi, then average of xi is what? You sum it up. So, summation of all xi divided by the number which you have. So, what will be the summation? 2 plus 2, 4 and then 16, and you have 20, so 36. And how many numbers you have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So, it will be 4. Very easy, that all of you know. Now, we can take the average in the other way is that instead of taking summation of xi, you say 2 times 2 plus 3 times 4 plus 4 times 5 and then divide by 9. This will also give you the average value. So, this summation you can write as summation of ni xi, where ni gives you the number of times the number appears. So, this divided by n, or you can write this equation as summation ni divided by n into xi. And what is ni divided by n? Ni divided by n is probability. How many times 2 is appearing, how many times 4 is appearing, okay. So, 2 times 2 is appearing, so 2 divided by 9, 3 times 4 is appearing, so 3 divided by 9, okay, and 4 times 5 is appearing, so 4 divided by 9. It gives you the probability in which it is appearing. And what is the probability in quantum mechanics? Probability in quantum mechanics is psi multiplied by psi square. So, that is why you have psi star, and for very infinitesimal values these summations could be approximated to integrals. So, we approximate and we get this value. So is the average value postulates in quantum mechanics. So, the only thing is that if the wave function is not normalized, then also you can find out the average value, but you will have to keep this denominator. Otherwise, if wave function is normalized, you can omit this denominator, you can calculate it from this equation itself. Okay. So, this is your postulate number 4. Then comes the next postulate, that is the last postulate, postulate number 5. It talks about the change in the wave function with respect to time, okay, and the equation which is given as del psi by del t is equal to h psi, okay. This is called time dependent Schrodinger wave equation, time dependent Schrodinger wave equation. Or you can write this as I h cross del psi by del t, and now what is h Hamiltonian? H cross square divided by 2m del square plus v into psi. Okay. So, this talks about the dynamics of the system, how with passage of time the wave function will change, dynamics of wave function. Means if wave function is changing, other properties will also change. Okay. But we throughout this quantum chemistry course, we will not be concerned with the dynamic system. So, we will not use time dependent Schrodinger equation, but those phenomena for which you need to know that time average or the dynamics of the system, then you can use this equation also. Okay. So, these are the 5 fundamental postulates of quantum mechanics. Postulate 1 about wave function, postulate 2 about operators, 3 about eigenvalue equations, 4th about average value or expectation value, and 5th is the time dependent Schrodinger wave equation. We will not use this 5th postulate, but rest of the postulate we will use time and again. Okay. Now, having done this fundamental, having learned these postulates of quantum mechanics, the next goal is to apply this Schrodinger wave equation to a particular system, and the system which we will be using will be broadly grouped into 2. It will be a model system or a real system. Okay. So, the systems which we will be doing will be model system and real system. We will do several model systems, but only one real system will be the hydrogen atom. Okay. But before we do that and we take up every system in details, let us see how does this equation behaves. Say for example, if you have if you write the Schrodinger wave equation for a system where you have only translational motion, no rotational motion is present, and the particle is moving in only one line in a straight line, then how can we write the Schrodinger wave equation? So, let us write it. The Schrodinger wave equation for one dimensional system could be written as minus h cross square divided by 2m ds square by dx square psi plus v psi is equal to E psi. Okay. Now, assume that particle is free. Free to move in one dimension. It does not have any limit, it can move in one dimension, no force is acting. So, in that case, for a free particle, when there is no force involved, then the potential energy V will be equal to 0, and you will have minus h cross square divided by 2m ds square by dx square psi is equal to E psi. We can rearrange this equation and we can write ds square psi by dx square is equal to minus 2m divided by h cross square E into psi. If I write this 2m E divided by h cross square as kappa square, this I can write, or this we can write very easily. Okay. Now, we have a double differential equation ds square psi by dx square plus k square psi is equal to 0. So, what will be the psi value? What will be the solution for this equation we have to find out. In order to do that, we write first the solution and then we check this solution is valid or not. So, we can write, what we can write is, one of the solution I can write as psi is equal to a exponential I k x plus b exponential minus I k x, where a and b are constants. Okay. So, in order to check it that whether this will be the solution or not, what you do? You double differentiate this equation. So, do first differentiation d psi by dx, and what do you get? You get a I k exponential I k x, okay, and then you can write plus b minus I k exponential minus I k x, okay. Then you do second differentiation, and what do you get? You get a I square pi square, then exponential I k x, then you do b, so minus and minus will be plus, and again you will have I square pi square exponential minus I k x, okay. And if I square is minus 1, so I write minus pi square is common, then you have e exponential I k x plus b exponential minus k x. So, this is what? This is actually psi from here. So, you can write, you get the equation back. So, one of the possible solution of, I will write Schrodinger wave equation, for this Schrodinger wave equation is psi is equal to a exponential I k x plus b exponential minus I k x, okay. And if this can be the solution, there are other possible solutions also. Let us see what is the other possible solution. We can write the wave function psi as c sin k x plus d cos k x also. Remember, our equation was d square psi by dx square plus kappa square psi is equal to 0, and we need to find out the solution for this equation, okay. So, again in the same way you check this, you do the d square psi by dx square and find the value, d square d psi by dx and then you do d square psi by dx square, and what you will find it is that again you get minus k square into c sin k x plus d cos k x, and that will be the solution. Knowingly I have left this part, you do, those of you mathematics can do it, you can do it very easily, okay. So, this is again, so two solutions we have, one is a exponential I k x plus b exponential minus I k x, and another is c sin k x plus d cos k x. What are these constants a and b and c and d? Let us try to understand these constants value, okay. And even one of this will be the solution. So, suppose if I write psi is equal to a exponential I k x, and when I write this, I suppose b to be equal to 0. Okay, and this also you can check. You do d psi by dx, and it will be a I k exponential I k x, and then again you do d square psi by dx square. You will have a I square kappa square exponential I k x. Okay, and then minus kappa square a exponential I k x. So, this is also one of the solution. This is psi, so you get minus kappa square psi. Okay. So, any one part, this part could also be the solution, this part could also be the solution. So, now if when I write this one, I suppose b is equal to 0. Okay. So, from the solution psi is equal to a exponential I k x plus b cos minus b exponential minus I k x. Okay. We let b is equal to 0, and then your solution, your equation becomes I k x. Try to find out the momentum from this one. How will you find out? You will use the operator. So, the operator for momentum p x is h cross I and d dx. So, try to find out an eigenvalue equation like this one, p x psi. So, p x psi means you have h cross I d dx of a exponential I k x. Okay. And what will you have? You will have h cross I, and if you differentiate it, what do you get? You get a I k into exponential I k x, and if I rearrange this, what do you have? You have h cross square k, then a exponential I k x. So, if you operate with an operator on a wave function like this one, what you have? Your wave function was a exponential I k x. Okay. When you operate with p x on this function, you get the function back with a constant. So, this will be the eigenvalue. It is an eigenvalue equation. Okay. We say that a into exponential I k x is an eigenfunction of p x operator. Okay. And the eigenvalue is value of p x is h cross kappa. This we have determined when b is equal to 0. You can go for other way also. Let a is equal to 0, and if that is so, then psi will be equal b exponential minus a kappa x. So, apply the same operator, play with the same operator, p x operator. So, what is p x psi now? P x psi is h cross I d dx of b exponential minus I kappa x. And for that, now you will have h cross k, and you have minus sign also, minus, and then b exponential minus I k x you will have. So, again you get the function back. When you apply with an operator on this function, you get the function back with a constant value, but this time you have a negative sign also. Okay. So, this is again a eigenvalue equation, and this time the eigenvalue is minus h cross k, and what this, so this is the value of x component of the momentum. So, if you suppose b is equal to 0, you get momentum h cross k. If you suppose a is equal to 0, you get momentum minus h cross k. So, and momentum is a vector quantity. So, that vector quantity, so this sign of the momentum tells you that if in one case the particle is moving in this direction, then in another case the particle is moving in this direction. Of course, on the single dimension, one dimension we are talking about. Okay. So, the coefficients does have a very important role to play. Coefficient, by assuming b is equal to 0, you say that momentum is, if this is your plus h cross k, then this will be minus h cross k. So, direction of the particle movement one can talk about by talking about these coefficients. Okay. What about the energy of such particles? Because here what we have supposed? We have supposed that the particle is free, there is no force acting on it. Okay. And what was the, let me write it again. What was the equation? The Schrodinger wave equation was minus h cross square divided by 2m in one dimension ds square by dx square. V was 0. So, we have written E psi, and then I said you ds square psi by dx square was minus 2m divided by h cross square E psi, and this was equal to, so kappa was equal to root under 2m E depending upon h cross square. Okay. So, if you try to find out kappa square, sorry, this was h only. If you want to find kappa square, then it was 2m E divided by h cross square. So, if I write kappa square h cross square divided by 2m, this will be equal to energy. Okay. And there is no boundary condition, particle is free to move. So, there is no limit to the energy also. The particle is free to move in along one dimension, and there is no limit to the value of energy also. Okay. And so, we say that a free particle can have any amount of energy. Okay. What will happen if you restrict this particle to move in a small space? Okay. So, let us see what happens then. Okay. If you say that the particle can move from this line to this line only, from 0 to a only, on this dimension x dimension. Okay. And again the particle potential energy we suppose equal to 0, and we suppose this to be infinity, potential energy on this side is infinity. Okay. And if it is so, then we say such system to be infinite potential wave, or the simplest problem particle in a one dimensional box. So, we will see this in the next class, that how do we apply Schrodinger wave equation to particle in a one dimensional box. Okay, thank you.